An atmosphere is the gravitationally bound layer of gas that surrounds a planetary body, and whether a world keeps one at all depends on a long, slow competition. On the supply side are the processes that add gas, volcanic and impact outgassing from the interior, the capture of gas directly from the young sun's nebula, and the sublimation of surface ices. On the loss side are the processes that remove it, escape to space, chemical reaction with the surface and condensation. The single principle that governs the shape of every atmosphere from the crushing air of Venus to the faint wisp around Pluto is hydrostatic equilibrium. At every height, the upward push of the pressure difference across a layer exactly balances the downward pull of the weight of gas above it. Because the gas is densest at the bottom and thins with altitude, this balance forces pressure to fall smoothly and continuously as you rise. It is the same balance that holds a star together, applied to a thin gaseous shell, and it is the foundation on which all the rest of atmospheric physics is built. Combining that balance with the ideal gas law, the relation between a gas's pressure, density, and temperature yields one of the most useful results in all of planetary science. Pressure falls off exponentially with height. The vertical distance over which the pressure drops to about a third of its value is called the scale height, and it is set by just three things: the temperature of the gas, the mass of its molecules, and the strength of gravity. Warm, light molecule atmospheres on low-gravity worlds are puffy and extended. Cold, heavy molecule atmospheres on massive worlds are compact. For Earth, the scale height is about 8.5 kilometers. For Mars, whose air is almost entirely carbon dioxide and whose gravity is weak, it works out to around 11 kilometers, so the thin Martian air actually thins with altitude more gently than one might guess from its feeble surface pressure. Scale height is the ruler of an atmosphere. It sets the thickness of cloud decks, the vertical span of haze, and the amount of air that starlight must pass through. Stacked vertically, atmospheres divide into thermal layers, defined by whether temperature rises or falls with height. Earth has 5. The lowest, the troposphere, holds about 80% of the atmosphere's mass and nearly all of its weather. Heated from below by the sunlit surface, it overturns by convection and cools steadily with height. Above it, the stratosphere does the opposite, growing warmer with altitude because its ozone soaks up solar ultraviolet, and that warm-over-cold inversion makes it very stable and quiet. Higher up, the mesosphere is the coldest layer of all, and above it the thermosphere is heated by extreme ultraviolet and X-ray photons to 2,000 degrees or more, though its gas is so thin that this fierce temperature carries almost no real heat. The outermost exosphere is so rarefied that atoms follow free ballistic arcs, and the fastest of them escape entirely. Other planets repeat the pattern, a convecting lower layer capped by radiatively controlled upper ones. Wherever an ultraviolet absorber warms the middle atmosphere, a second division cuts across the thermal one, this time by composition. Below about 100 kilometers on Earth, turbulent eddies stir the air so vigorously that all the major gases stay well mixed in fixed proportions in a region called the homosphere. Above it, turbulence dies away and each kind of molecule settles out under its own weight, so the heavy molecules thin out fastest and the lightest species, atomic oxygen, then helium, then hydrogen, come to dominate at successively greater heights. This quiet sorting by mass is why escape, when it happens, is overwhelmingly a story of the lightest atoms reaching the top first. The upper atmosphere is also partly ionized by solar ultraviolet and X-rays, forming the ionosphere, a shell of electrically charged gas whose free electrons reflect radio waves back to the ground, and whose currents, steered by the planet's magnetic field, light up the aurora. The temperature profile of the lower atmosphere is not arbitrary. It is set by a contest between radiation and convection. If radiation alone would leave the air with too steep a temperature drop from bottom to top, the arrangement becomes top-heavy and unstable, and the gas simply overturns, carrying heat upward far more efficiently by bulk motion. The critical steepness at which this begins is the adiabatic lapse rate, the rate at which a rising pocket of gas cools purely because it expands into the lower pressure above, trading no heat with its surroundings. For dry air on Earth, this cooling comes to about 10 degrees for every kilometer of ascent, fixed by the ratio of gravity to the gas's heat capacity. When the rising air is moist, its water vapor condenses as it cools and releases latent heat, partly offsetting the chill, so the moist rate is gentler, around 6 degrees per kilometer. Earth's actual average, about 6.5 degrees per kilometer, sits between the two, reflecting a partly moist, convecting troposphere. Meteorologists judge stability with a clever bookkeeping device called potential temperature, the temperature a pocket of air would have if it were brought, without gaining or losing heat, down to a standard reference pressure. Where potential temperature increases with height, the atmosphere is stable and resists overturning. Where it decreases with height, the air is unstable and convects, and the rate at which a nudged parcel bobs back toward its rest level measures how stiffly the layer is stratified. This framework explains the whole layered architecture. The troposphere is the convecting layer, held close to the adiabatic rate by its own overturning, while the stratosphere, warmed from above by ozone, has its potential temperature rising steeply with height and is, therefore, strongly stable and almost free of vertical mixing. The very same physics governs Jupiter's deep, vigorously convecting hydrogen envelope and the convective methane weather of Titan. Only the gas, the gravity, and the condensing substance change from world to world. Composition is the chemical fingerprint of how an atmosphere was born and how it has aged, and it comes in two broad classes. Primary atmospheres are captured straight from the gas of the solar nebula, and so are dominated by hydrogen and helium, nearly the Sun's own proportions. The giant planets still wear these. Secondary atmospheres are made after a world forms by outgassing from the interior and the delivery of ices from outside, and are built from heavier molecules like carbon dioxide, nitrogen, and water. The rocky planets and larger moons have these. Earth's dry air is about 78% nitrogen, 21% oxygen, 1% argon, and only a whisper of carbon dioxide, 0.04%. That oxygen is biological, the exhaust of photosynthesis, and it keeps Earth's air chemically far out of equilibrium. Venus and Mars are both almost pure carbon dioxide, differing 100-fold and more in pressure, while Titan alone among the moons wears a thick atmosphere of mostly nitrogen, the only one besides our own. Buried in the composition is a running record of everything the atmosphere has lost, written in the ratios of isotopes, because the lighter version of any atom escapes a little more easily than the heavier one. The clearest example is at Venus, where the ratio of heavy hydrogen, deuterium, to ordinary hydrogen is enriched roughly 100 to 150 times above the Earth's value. That single number is the strongest evidence that Venus once held the equivalent of a substantial ocean, whose water was later broken apart by sunlight so that the light hydrogen leaked away and left the heavy behind. In the same way, the argon isotopes measured at Mars record how much gas has been sputtered off into space. Composition, in other words, is never a fixed inheritance. It is the running total of supply, chemistry, and loss, added up over billions of years. The temperature of a planet's surface is set at the coarsest level by a simple energy balance. The sunlight it absorbs must equal the thermal infrared it radiates away. A planet catches sunlight over its shadow-sized disk but radiates from its entire globe, and balancing the two gives what is called the effective temperature, the temperature at which the world glows to space. For Earth, allowing for the roughly 30% of sunlight it reflects, this effective temperature comes out around 255 Kelvin, which is well below the freezing point of water and a full 33 degrees colder than the actual global average surface temperature of 288 Kelvin. That 33-degree gap, the difference between the temperature at which Earth radiates and the warmer temperature it actually enjoys at the ground, is the greenhouse effect, and it is the reason the planet is habitable at all. The mechanism is one of radiative transfer through a partly opaque gas. The greenhouse gases, chiefly water vapor, carbon dioxide and methane, are nearly transparent to the incoming visible sunlight, but strongly absorbing to the outgoing infrared. So they intercept the heat, radiation rising from the surface and re-emit it in all directions, sending roughly half of it back downward and forcing the ground to run hotter than sunlight alone could manage. A useful way to picture it is that there is always some level high in the atmosphere from which the infrared finally escapes freely to space, and that level is pinned near the effective temperature by the energy balance. Adding more greenhouse gas pushes that escape level higher into thinner, colder air, and because the surface is tied to it by the steady temperature drop of the troposphere, the whole column beneath warms. This is why increasing carbon dioxide heats the surface, even though the top of the atmosphere must always radiate at the same fixed temperature. There is an important subtlety in how the absorbing gases work. They do not swallow infrared evenly across the spectrum, but in discrete bands. When a band is already nearly opaque at its center, adding still more gas can only deepen the absorption at the band's weak edges, so the extra warming grows only in proportion to the logarithm of the concentration, not in direct proportion to it. For carbon dioxide on Earth, each doubling of the amount adds a little, under 4 watts to every square meter, whatever the starting point. This slow, logarithmic growth is exactly why carbon dioxide stays a powerful climate lever even at high abundances, and why Venus, with an atmosphere 92 times heavier than Earth's and almost all carbon dioxide, reaches a surface temperature of about 737 Kelvin, hot enough to melt lead, even though its bright sulfuric acid clouds reflect most of the incoming sunlight and leave it absorbing less than the Earth does. Ordinarily, the greenhouse is a stabilizing influence, but where water is involved, it can turn catastrophically unstable. The amount of water vapor that air can hold rises very steeply as it warms, and water vapor is itself a strong greenhouse gas, so a warming surface loads the air with more vapor, which warms the surface further, which loads in more vapor still. On today's Earth, this loop is safely damped, but there is a hard ceiling built into the physics. Once an atmosphere becomes saturated with water vapor all the way up, the infrared it can radiate to space stops rising with surface temperature and levels off at a fixed maximum, because every radiating layer is now sitting on the same water vapor curve. If the absorbed sunlight ever exceeds that maximum, no surface temperature can balance the books at all. The oceans boil away entirely and the planet enters a runaway greenhouse. The exact value of that radiation ceiling is still debated and refined with climate models, but the existence of a hard limit is robust, settled physics. Venus is the archetype of that runaway. Orbiting close enough to receive nearly twice the sunlight that reaches Earth, the young Venus is thought to have crossed the threshold, boiled off whatever oceans it had, and lifted its water high into the atmosphere where ultraviolet light split it apart. The light hydrogen escaped to space, and the oxygen was left to react with the rocks. The enormous enrichment of heavy hydrogen that remains today confirms that a whole ocean's worth of water was lost this way in the planet's first few 100 million years. With its water gone and its carbon left in the air rather than locked into rock, Venus settled into the 92-bar lead-melting furnace we find now. Earth, sitting just a little farther from the Sun, never crossed the line. Its carbon was steadily buried as carbonate rock by the weathering cycle, holding carbon dioxide and temperature in a moderate, life-friendly range. That divergence of two nearly twin planets is the central cautionary tale of planetary climate. Atmospheres do not only trap heat, they leak, and the rate of that leak decides how long an atmosphere survives. The simplest loss channel is thermal escape, powered by the fast-moving tail of the gas's own heat motion. Deep down, molecules collide too, often to get anywhere, but density falls off with height, and at a level called the exobase collisions become so rare that a fast atom heading upward can sail clear into space without being turned back. Whether it escapes depends on whether its speed exceeds the planet's escape velocity, and the governing quantity is the ratio of a molecule's gravitational binding energy to its thermal energy, known as the Jeans parameter. When that ratio is large, for a heavy molecule on a cold or massive world, only the very fastest atoms in the extreme tail can escape, and the atmosphere leaks only slowly, one molecule at a time. This is exactly why Earth holds on to its nitrogen effortlessly, yet steadily loses its lightest gases, hydrogen and helium, to space. The dependence on molecular mass is astonishingly sharp, because the escape rate falls off exponentially as that binding to thermal ratio grows. On Earth, the numbers fall so that hydrogen escapes appreciably, while nitrogen, only 28 times heavier, is for all practical purposes bound forever, and the preferential loss of the light gases is just what leaves the survivors enriched in heavy isotopes. The same arithmetic explains why the Moon and Mercury, with their feeble gravity, cannot hold an ordinary atmosphere at all. And when that ratio drops low enough, escape changes character completely. Rather than trickling away atom by atom, the whole upper atmosphere heats under intense ultraviolet and streams outward together as an organized wind, a process called hydrodynamic escape or blow-off. Such an outflow can run orders of magnitude faster than the slow molecular leak and can drag heavier atoms along with the fleeing hydrogen. It is thought to have stripped the early hydrogen-rich air from the young rocky planets, and it still operates fiercely on close-in exoplanets and gently on Titan and Pluto. Many atmospheres lose gas faster than heat alone can explain, through a family of non-thermal processes that hand atoms their escape energy by other means, solar ultraviolet and the solar wind can drive reactions that fling out fast atoms, can crash charged particles into the upper air to knock atoms loose like the break in a game of billiards, and can seize newly ionized atoms and sweep them off on the solar wind's electric field. These channels dominate the loss of heavier atoms like oxygen and carbon, for which thermal escape is hopeless. Mars is the defining case, and NASA MAVEN orbiter, working since 2014, was built precisely to measure them. Because argon is inert and can only be knocked out by that physical sputtering, the enrichment of its isotopes is a clean clock, and from it the team concluded that about 65% of all the argon Mars ever had has escaped to space, and with it most of the planet's original carbon dioxide, stripped away when the young sun blew far more fiercely than it does today. Mars did not simply freeze, it was actively eroded. That erosion is still coupled to the daily weather. MAVEN has tied Mars's great global dust storms to surges in escape. The suspended dust heats the atmosphere, lofts water vapor to high altitudes where sunlight can break it apart and stirs up waves that ripple into the upper air, so that during a major storm the hydrogen escape can transiently double or triple. The Martian atmosphere, in other words, is not a dead remnant but a living system whose leak rate breathes with the seasons, the dust cycle, and the 11-year rhythm of the sun. Even Venus keeps surprising us. A study in 2024 found that the dominant way it loses hydrogen today runs through a particular ionospheric reaction that earlier work had missed, roughly doubling the estimated rate. Atmospheric escape, it turns out, is not one process but a whole portfolio, and even for the best-studied planets the accounting is still being corrected. Turn from what atmospheres lose to how they move, and you find that every atmosphere is a heat engine. Because a planet is heated most fiercely at the equator and least at the poles, the resulting temperature difference drives a great overturning that carries heat poleward. In its simplest form, first sketched by George Hadley in 1735, the air rises in the hot tropics, streams poleward high up, sinks again in the subtropics and flows back toward the equator along the surface, but on a briskly rotating planet like Earth this loop cannot reach all the way to the pole. As the poleward moving air aloft conserves its spin, the Coriolis effect swings it sideways into powerful west-to-east jets, and the overturning cell is confined to the tropics, petering out near 30 degrees of latitude. Beyond that, the work of carrying heat poleward is handed off to the migrating high and low pressure systems, the eddies that make the weather of the middle latitudes. The balance between a planet's spin and its winds is captured in one number, the Rossby number, the ratio of the wind's own inertia to the deflecting Coriolis force. When it is small, rotation rules, and the winds settle into what is called geostrophic balance, blowing nearly along the lines of constant pressure rather than straight across them. Slowly turning worlds have broad cells reaching almost to the poles, fast spinners like Earth have narrow tropical cells and turbulent, storm-filled middle latitudes. The most spectacular circulation of all is superrotation, in which the whole body of the air laps the planet far faster than the solid globe beneath. Venus is the showcase. Its surface takes 243 Earth days to turn once, yet its cloud tops race around in about some 60 times faster. Just how that is created and sustained is still one of the real unsolved problems of planetary meteorology. Titan superrotates too, and the giant planets spin their atmospheres into the alternating east-west bands we see as their belts and zones. Sunlight does more than warm an atmosphere. Its ultraviolet photons snap chemical bonds and drive a photochemistry that reshapes composition with height. Earth's showpiece is the ozone layer, explained by Sidney Chapman back in 1930. Hard ultraviolet first splits molecular oxygen into single atoms. Each atom joins another oxygen molecule to build ozone. The ozone then absorbs softer ultraviolet and splits again, in a self-renewing cycle that shields the surface from damaging rays and in the process warms the stratosphere and creates its temperature inversion. Trace pollutants, including the chlorine freed from industrial refrigerants, can catalytically tear ozone apart far faster than the natural cycle rebuilds it, which is the chemistry behind the Antarctic ozone hole, but photochemistry can build as well as destroy. On Titan, sunlight breaking up methane sets off a chain that assembles ever larger organic molecules, raining down the thick orange haze of tholins that cloaks the moon. New Horizons found layered hazes, towering high above Pluto, and on the giant planets methane chemistry paints the stratospheric smog and in part the colors of the clouds. Set the world side by side, and the full range of atmospheres comes into view. At the thinnest extreme are the surface-bounded exospheres of Mercury and the Moon, so tenuous that an atom leaps from the surface and flies clear to another patch of ground without ever colliding. These are the faintest of clouds, sodium and potassium and helium knocked loose from the rock by sunlight, by the solar wind, and by the vapor of micrometeoroid impacts, and then endlessly recycled. The rocky planets span 4 full orders of magnitude in surface pressure, from the 6,000ths of a bar on Mars, a quarter of which freezes onto the winter pole and sublimes back again each year, through Earth's single bar, up to the crushing 92 bars of Venus, and yet their wildly different surface temperatures, 210 Kelvin, 288, and 737, are set almost entirely by the mass and the infrared opacity of the air above them, exactly as the greenhouse physics demands. The giant planets are another regime entirely, wearing deep primary envelopes of hydrogen and helium that have no surface at all but simply thicken downward into fluid interiors, their visible weather organized into banded belts and zones, and dotted with storms like Jupiter's great red spot, wider than the Earth and centuries old. And out in the cold, the outer moons and dwarf planets hold delicate atmospheres balanced against their own surface ices, from Titan's thick nitrogen air, dense enough to walk through, with its full cycle of methane clouds, rain, rivers and lakes, to the tenuous nitrogen wisps of Pluto and Triton, which thicken and fade as the distant sunlight shifts across their frost. Across that whole enormous range, from a few stray atoms drifting above Mercury to a supercritical fluid at the foot of Venus's atmosphere, the same short list of principles, hydrostatic balance, radiative-transfer, escape, and the dynamics of a rotating fluid, governs all of it, that a handful of physical laws can stretch to fit every gaseous envelope in the solar system and the thousands now being found around other stars, is exactly what makes the physics of atmospheres such a powerful and testable science.